Hey guys, this is going to be our second example on Centripetal Force, and in this problem, we can go ahead and get started. In a popular amusement park ride, a cylinder of radius 2.1 meters is set in rotation at an unknown speed. The coefficient of static friction is 0.4. In a twist of events here, the floor drops away, leaving the rider suspended against the wall in a vertical position. What minimum speed v must the cylinder and rider have if the rider is not to fall and the floor drops? Some of you guys might be able to relate to this ride. It is sort of a popular amusement park ride. I only do know it by one name. I think it does go by multiple names though. But the name I've always known it to be is it's called a gravitron, and based on the ride, it does spin at a very rather high speed. And if you've ever been on this ride, if you ever attempt to kind of raise any body part up, you can find that the force is very strong. It keeps you kind of pinned down upon the wall with a really strong force. But anyway, so couple information we're given here is the radius of the cylinder is 2.1 meters. So let me draw the radius up here, because I'll need the room later. So the radius of the cylinder is 2.1 meters. Right, that's R, and radius is 2.1 meters. The coefficient of static friction is going to come into play in just a bit. It's also important to note that where is the rider in this ride? Well, they are pinned against this wall, right, and there is no floor. So let's go ahead and draw a free body diagram located right here. One of the forces that are present in this is going to be force of gravity. Right, it's typically always present, and it's going to be drawn in that manner. So we'll have a force vector going that way. So we'll call this Fg. Now there are two other forces present in this. There is no floor. Right. So we can't say that there is a normal force that is opposite to the force of gravity. However, there is a surface in our problem, and that surface happens to be the normal force. I'm sorry, no. That surface happens to be the wall. Right. And that wall that's keeping us inside this ride is acting like the normal force. If we move the wall and the ride continues in the same manner, the rider would be thrown out of this amusement park ride. So this wall, which we'll call the normal force, is keeping us in this circle. So let's go ahead and draw like so. Alright, and we'll call that the normal force. And we'll call this Fn. Now you might look at our free body diagram and say, well, alright, fine, we have a normal force, it's aimed to the center, right, and what else is present? Because based off our diagram, this would imply that our rider is going to fall. Alright, if the force of gravity is the only force present in our problem. Alright, so that's going to be a huge issue, because we don't want the rider to fall. And so there has to be something that keeps a rider in the ride. Okay, and for that to happen, there has to be a force in the opposite direction of gravity. Obviously, it's not the floor, because the floor is gone. So what is this? What are we relying on left? Well, if we're pressed against this wall, there is a surface contact. All right, we're talking about surface contact here. There's only one force possible left, and that is friction. It's not kinetic friction because we're stationary. It has to be static. Static friction is a friction that keeps objects from moving. So static friction would be in that direction. Alright, and let's go ahead and label this as friction. We'll label it as FFS. So static friction has to counteract the force of gravity in this problem. Alright, so if we look at this, the only centripetal force there is the normal force. Alright, so the wall of the ride is the only reason the rider is kept in a circular motion. So perhaps we could say something like this. Alright. We would have to say the normal force is the centripetal force. Alright. So if the normal force is the centripetal force, and we know what centripetal force is defined by, centripetal force is defined by the mass of the object times the tangential speed squared over the radius. Right? And the centripetal force is the normal force. Now we're used to saying that the normal force is equal to the force of gravity because, if an object is on the surface, the normal force is to the opposite of the gravity. But this isn't the case. Let's go ahead and look at what is the relationship between normal force and static friction. Well, if you recall, now right on up here, the relationship between static friction, force of friction static, this is equal to the coefficient of static friction by the normal force, the surface that it's in contact with. Well, the force of friction, we're relying on this to keep the object, or not the object, the rider in the ride. Right. So if the force of friction is not enough, what happens is the force of gravity is going to cause the rider to fall out. So what we want is the force of friction to match the force of gravity for the rider to be stationary. So what we want to say based off our free body diagram is that the force of friction static has to equal to the force of gravity for the rider to be still. Well, that's true. Then we can also say that force of gravity equals to the coefficient by normal force. But we know what force of gravity is defined by. Force of gravity is defined by mass times mg. Okay, coefficient by normal force. Right. So if this is the case, well, then the normal force really is defined by mg divided by the coefficient. That's the normal force in our problem. And we can take this expression and say this. We can take this expression because that's the normal force in our problem. what this looks like now is mg, mass times gravity divided by the coefficient of static friction, equals to the centripetal force, which is mass times Vt squared over r. Alright, so we need to figure out what is the speed necessary to keep the person in the ride. Well, we can kind of just drop mass here, and if we isolate the tangential speed, let's see what we get here. The tangential speed equals to gravity times the radius of the ride divided by the coefficient of static friction, and of course square root. Alright, and we have gravity, and we have the radius, and we also have the coefficient of static friction, and this will allow us to find the speed necessary for the rider to stay in this without falling out. Alright, and that's it for this problem.